Okay, so today we're going to be able to determine whether an improper integral converges by comparing it to another integral whose convergence behavior we know. Today is also the first of several days where we learn to write proofs. So last class we handled some improper integrals. In each case we were able to find an antiderivative. And the way we handled it was we just integrated, instead of from 0 to infinity, we would integrate from 0 to b, and then take the limit as b goes to infinity. But that all hinged on being able to evaluate the antiderivative. So today we're going to work on improper integrals where you can't find an antiderivative. It's just too hard. So our big conclusion from last class, you worked on several activities that led us to this conclusion. If you integrate from any positive number to infinity of 1 over x to the p dx, that converges when p is bigger than 1, and it diverges when p is less than or equal to 1. But it's the opposite if you integrate from 0 to a positive number. 1 over x to the p dx converges when p is less than 1 and diverges for p greater than or equal to 1. So we're going to be using that a lot today. Okay, so suppose that you have two functions, f and g. They're both positive. They're both always above the x-axis, and f is smaller than g for x after some x value. So here's an example. For what values of x is f less than or equal to g, according to this graph? After 1, yeah. After x equals 1, the graph of f is below the graph of g. So if I wanted to solve this inequality, f is lower than g. The y values of f are smaller than the y values of g when x is bigger than or equal to 1. At 1, they're equal, and then after that, f is always smaller than g. Okay, so using this image where f is smaller than g after 1, if I want to integrate from some number a to infinity, so let's just put a in a random spot here, like that. Okay. If I know that the integral from a to infinity of g of x dx converges, so I know that the area under g from a to infinity is finite. That is some finite number. What can I conclude about the area under f from a to infinity? What do you think? Yeah, it's also finite because it's smaller than a finite number. Yeah. So if the integral from a to infinity of g of x dx converges, that means it's finite. It means it's just some number. And the integral from a to infinity of f of x dx is smaller than some finite number. Yes, in this case, it's strictly less than, but or it's still true if we put the or equal to, because it's less than or equal to. The or is not inclusive. Yeah. So that means if that integral is smaller than a finite number, it has to also be finite. So my conclusion, what can I conclude? That the integral from a to infinity of f of x dx also converges, right? Without having to do any calculations with the limit as b goes to infinity and taking an antiderivative, I know that f of x has to converge because the area under f is smaller than the area under g, and I know that the area under g is finite. All right, let's look at the reverse. Let's say I know something about the area under f, the integral from a to infinity of f of x dx. Let's say that area diverges. That area is infinite. If that integral diverges, the area under f is infinite, what can I conclude about the area under g? It also has to diverge, yeah. because the area under G is larger than the area under F, and the area under F is infinite. If you're larger than infinity, you are infinity, right? Okay, so I can say if this integral diverges, that means that this integral is infinite. The area under the curve is infinite. Okay, so that means that the area under G is larger than something infinite, which means it also diverges. So my conclusion is that the integral from a to infinity of g of x dx also diverges. This is called the comparison test. We'll be sure to refer to it by name whenever we use it. So you can show that an integral converges if you can find a larger convergent integral. You can show an integral diverges if you can find a smaller divergent integral. Yes.
Would we be able to say that the area between the area under f of x and g of x, like that little sliver,
yeah, good question.
Like,
yeah. You know it was finite. If you know G, yeah, okay, so the question is about this little sliver between F and G. If you know G converges, then that sliver definitely is going to be finite. Yeah. If you know G diverges and F diverges, I'm pretty sure that that little sliver is going to be, I don't think we can make a conclusion about it. Yeah, I don't think we can. In the instance where both G and F are divergent. I think it's possible that it would converge and we would have to do a totally other analysis on it. Yeah. Okay, so in practice, what we try to do is figure out a simpler function than the one in question, but that has a similar end behavior. And then we look to compare it to our complicated thing. Okay, so useful integrals we can use for comparison are the 1 over x to the p integrals that we had our big conclusion about last class. So you know the convergence, divergence behavior for 1 over x to the p. And 1 over e to the ax. It converges when a is positive and diverges when a is negative. Okay, so those are useful integrals for comparison. Here's an important fact. If a is bigger than b, then 1 over a is smaller than 1 over b. Right? For example, 12 is bigger than 5. So when you take the reciprocals, 1 over 12 and 1 over 5, 1 over 12 is smaller than 1 over 5, right? Bigger denominator makes a smaller fraction. Okay, so let's practice, see how this works. Determine the convergence or divergence of these integrals. So I've got a 4x squared on top. I'm going to pull that 4 right out of my integral. It's just complicating this. So this is going to become 4 times the integral from 1 to infinity of x squared over x to the 4th plus 4x plus 1 dx. Okay, so I need something to compare to. That is really hard to integrate. I can't take an antiderivative and just do this directly. So I want to compare this to something that's got a similar end behavior to the integrand. So I'm going to compare to the integral from 1 to infinity of 1 over x squared dx. How did I come up with 1 over x squared? The leading terms, yes, the leading terms of the numerator and the denominator. X squared over x to the 4th. We're going from 1 to infinity, right? Infinity is huge. So the x squared and x to the 4th are going to be the dominant terms. Think about raising, a quadrillion to the 4th power. It's like huge. It's way bigger than 4 times a quadrillion. Okay, so the 4x plus 1 is kind of like whatever. When x is really big, it doesn't matter so much. So x squared over x to the fourth, that reduces to 1 over x squared. That's my comparison integral. So the integral from 1 to infinity of 1 over x squared, what does that do? Does it converge or diverge? It converges, yeah. So if you just go back to our comparison integrals, any positive number to infinity of 1 over x to the p, it converges when p is bigger than 1. So for us, p was 2, because this is 1 over x squared, so it converges. 2 is bigger than 1, it converges. So I'm going to say which converges. Okay, so if I can show that this function is smaller than 1 over x squared, then this integral is smaller than a finite integral, and I've shown convergence. Okay, so let's look at the two fractions. Oh, excuse me. Okay, x squared over x to the fourth plus 4x plus 1. I'm going to compare that to x squared over x to the fourth, because that's the same thing as 1 over x squared. So my numerators are the same, so I'm trying to fill in an inequality here. Numerators are the same, so that's not going to change the value. The denominator on the left, is that going to be larger or smaller than the denominator on the right? The denominator is larger, right? Because my x values are all between 1 and infinity. So if you plug in a large x value into x to the fourth plus 4x plus 1, it should be bigger than just x to the fourth. A little bit bigger, right? And when the denominator is bigger, the fraction value is smaller. So that's less than. Does that make sense? Okay. So my integrand is smaller than an integrand that converges on the same interval. So my integral is also going to converge. So I should write out like a final sentence here. So the integral from 1 to infinity of x squared over x to the fourth plus 4x plus 1 dx, that is smaller than the integral from 1 to infinity of 1 over x squared dx, which converges. You could say converges or is finite, if that helps you think about it. It helps me think about it. Okay. So my integral is smaller than a finite number, which means that my integral converges. Thus, the integral from 1 to infinity of x squared over x to the fourth plus 4x plus 1 dx is finite, and so converges. That is a proof, right? So I wrote some sentences. I proved to you that that integral converges. It is smaller than a convergent integral, so it has to also converge. Okay, let's try another one. The integral from 2 to infinity of 8 over the cube root of x squared minus 1. So the 8 doesn't really matter because if the integral is finite, 8 times a finite number will be finite. If the integral is infinite, 8 times infinity is still infinity. So the 8 doesn't matter, so I'm just going to pull it out of the integral and look at 1 over the cube root of x squared minus 1. All right, so I have to think about what to compare to. The integral from 2 to infinity compared to a similar integral on a similar interval. And I need something that I know it's convergence behavior, convergence, divergence behavior. So I think I'm just going to drop the -1. So this is going to be 1 over x squared cube rooted, which is the same thing as x to the 2/3. And then what does that do? Does that converge or diverge? It diverges because the p is less than 1. We're going from a positive number to infinity, 1 over x to the p. P is less than 1, so this diverges. Okay, so I need to compare my integrand to my comparison integral integrand. So let's look at the denominators, the cube root of x squared minus 1 compared to the cube root of x squared. What do I put here to compare the sizes of those two denominators? Which one's bigger? The one on the right is bigger, yeah. If you subtract 1 before you cube root, this is going to be smaller. So the one on the right is bigger. So that means that 1 over the cube root of x squared minus 1 compared to 1 over x to the 2/3. If the denominator is smaller here, then the fraction is bigger. So the inequality changes when you take the reciprocals. So that means that my integrand is larger than this integrand, which diverges, right? So my integrand is larger than an infinite integral. So I'm also going to have divergence. So let's write it all out. So the integral from, what was it? 2 to infinity of 1 over the cube root of x squared minus 1 dx is larger than the integral from 2 to infinity of 1 over x to the 2/3, which is infinite. Right? So the integral that I'm looking at is larger than an infinite integral, which means it is also infinite. Thus, the integral from 2 to infinity of 1 over the cube root of x squared minus 1 dx also diverges. The integral from 0 to 1 of 1 over the square root of x cubed plus x dx. So my comparison is just going to be 1 over, I'm just going to drop the x, the plus x. So I'm going to compare to the integral from 0 to 1 of 1 over x to the 3/2 dx, which, what does that do? Converge or diverge? It's different when the bounds are 0 to 1 than when the bounds are a number to infinity. It's like the opposite of what we've done so far. So this diverges because the bounds are 0 to 1. Okay, so now I need to compare my integrand to the comparison integrand. So 1 over x cubed plus x compared to 1 over x cubed. Both are square rooted. Okay, so let's look at the square root of x cubed plus x compared to the square root of x cubed. So I'm comparing the denominators here because the numerators are both 1. All right, which one is bigger? The left side is bigger. If you are at all unsure, pick a value in the interval like a half and plug in a half into both sides here. So just do this to give you a quick demonstration of it. So I'm going to do the square root. Okay. Square root of 0.5 cubed plus 0.5. And I get 0.79. And then I'm going to do the square root of 0.5 cubed. And that one is only 0.35. So, yes. So yeah, so I plugged in a number between 0 and 1. You have to plug something in the bounds, within the bounds of integration. Right. Yeah, you're right. So you do have to pick a number in the interval to see the truth of what's happening. So this is bigger, right? Which means that 1 over the square root of x cubed plus x compared to 1 over the square root of x cubed, the inequality reverses because now a bigger denominator makes a smaller fraction. All right, so my integral is smaller than the divergent integral. So let's just write this out. So the integral from 0 to 1 of 1 over dx, that is smaller than the integral from 0 to 1 of 1 over the square root of x cubed dx, which is infinite. Okay. So my integral is smaller than something infinite. What can I conclude? Can you say it louder? Nothing. You can have an integral that's smaller than infinity that's still infinite, or you could have one that's finite. You can conclude nothing. No conclusion via the comparison test. It does not help us. To conclude divergence, you have to be larger than something infinite. To conclude convergence, you have to be smaller than something finite. Being smaller than something infinite tells you nothing.